Okay. All right, so armed with this equation, first apparently solved by Wolfram, let's sorry? Yeah, first by Zeldovich, and, well, first, I guess it was solved by Zeldovich and explained by Wolfram. Yeah. Let's go ahead and just try to estimate what this solution will look like. So we have two limits here. In the limit that this cross-section is small, or it doesn't just have to be the cross-section, in the limit that these terms on the right-hand side are small compared to this dilution term, the Hubble dilution will dominate the evolution. And in that case, we'll just get back to the case with no annihilation that we saw before, that the number density is redshifting like 1 over a cubed. In the opposite limit, where this rate is extremely large, then we'll have a situation, as we discussed before, where the n is driven towards its equilibrium value, which is just determined by the temperature of the standard model bath. So when we solve this equation, what we'll generically see is that at early times, when the number densities are large, since this term scales like n squared, this term only scales like, and this term only scales like n, we'll see that we start out in equilibrium, and then at some point there is a crossover into this regime, and after that the number density just redshifts like 1 over a cubed, like you would expect of matter with no number changing interactions. That crossover point is called freeze out, because it's when the dark matter density starts redshifting just like matter without number changing interactions. So we characterize freeze out at least up to order 1 factors by requiring that this rate, n times sigma v, is comparable to Hubble, which is the same as saying that these two terms are parametrically of the same order. Okay, and I'm going to, so let's consider two, and I'm going to denote this with an F subscript. Also, the up-to-date, modern, and fully detailed version of this calculation, putting in all the order 1 factors that I'm dropping out here, can be found in this archive paper. Okay. So the first order picture of this calculation is that at early times, n is approximately n equilibrium. After freeze out, so after this condition is satisfied, we have, after this condition is satisfied, then n just goes as 1 over a cubed. So in other words, the solution at late times is that the number density goes like the number density at freeze out times the ratio of a factors at freeze out and at a later time. Now, we know that the number density at freeze out, up until freeze out, n approximately traces n equilibrium, so we can approximate this number density at freeze out by the equilibrium number density at freeze out. And we also know that to a first approximation, the temperature of the universe is just scaling like 1 over a, so we can write this, again, dropping all order 1 numerical factors like this. So basically, in order to work out the late time abundance of dark matter, we need to know the temperature of freeze out, and we need to know the equilibrium abundance at freeze out, and that's it. If we can do that, then we're done. So there are two broad cases here. The first case, which turns out not to work for dark matter, I'll give you the spoiler in advance, is where the dm is relativistic at freeze out. And hence, the equilibrium number density at freeze out is just the number density of a relativistic species, which goes like t cubed. So it's t freeze out cubed in this case. But in this case, this tells you that after freeze out, when I plug this in here, these two factors are just going to cancel, and no matter when the dark matter decouples, it's always going to be true. So this is the temperature of the universe, this is the standard model bath. It's always going to be true that the number density of the dark matter at late times is approximately the cube of the temperature of the CMB. So that tells us that this is also parametrically the number density of the photons in the universe. So this tells us that the DM number density for this hot relic is comparable to the photon number density. Now the photon number density is about 10 orders of magnitude larger than the baryon number density. So this would mean that the dark matter, there has to be 10 to the 10 dark matter particles for every baryon. But there's only 5 GeV worth of mass in dark matter particles for every 1 GeV of mass in baryons, right? The mass of the hydrogen atom is about 1 GeV. So this would mean that the mass of DM must be less than about 10 to the minus 9 times the baryon mass, which is about 1 GeV, to avoid having just too much dark matter to avoid overclosing the universe. So that tells you that in this case, we would need MDM less than about 1 eV in order for not to just have way too much dark matter, but remember the constraints that we just talked about before. If the dark matter was thermally coupled to the standard model, it decoupled while relativistic. We need the mass to be definitely larger than about 5 keV, and it's easier if it's larger than an MeV. This will mess up, this will disrupt structure formation and likely also Big Bang nucleosynthesis and the CMB. Like maybe you can get by with BBN if it's just like a scalar, if it's just a scalar particle, but this is very excluded. So this cannot be 100% of the DM. It's okay, this is called hot dark matter sometimes. It's okay for objects like this to be about 1% of the dark matter. That's not excluded, but it can't be all of that. Okay, so the other possibility, sorry, 1%, okay. I can give a reference to this if people are interested. So the cold relic is the case where the DM is non-relativistic. That frees out. So in this case, what's going to happen is that this n equilibrium at freeze out is going to have an exponential suppression. So according to this result. So this sounds good. Our problem here was that for high dark matter masses, we'd have way too much dark matter. So an exponential suppression in its abundance is a good thing. So let's see what we need to do to get the correct relic density in this case. So to get the right relic density, so the relic density just means the late time density, okay? So I could look up in the particle data group what the correct relic density is, but an easier way for me to parameterize this is to say, when our universe went through matter radiation equality, since the dark matter is most of the matter, I want the energy density in the dark matter to be comparable to the energy density in radiation at matter radiation equality, okay? So we'll require that the number density of the dark matter times the mass of the dark matter, this should be equal to this at matter radiation equality should be comparable to the total energy density in the CMB. And I'll call matter radiation equality MRE. Okay, so this is my requirement that okay. So now let's assume that this freeze out occurs in the radiation dominated epoch such that it's before matter radiation equality. Matter radiation equality occurs when the universe has a temperature of about 1 eV. So we'd like our dark matter in this thermal case to be significantly heavier than 1 eV. So let's assume for the moment that all this freeze out is occurring during radiation domination. Okay, so then we're going to require N MRE times MDM is approximately T MRE to the fourth. N MRE we can get from this expression. So this is N equilibrium at freeze-out times the temperature of matter radiation equality over the temperature of freeze-out cubed times MdM should be comparable to the temperature of matter radiation equality to the fourth. And we have another piece of information, which is this definition of freeze-out. So we know that at freeze-out, it has to be true that the Hubble parameter at freeze-out is comparable to N at freeze-out, which is approximately N equilibrium at freeze-out times sigma V. And we have another piece of information. So if we assume that this occurs during radiation domination, then we know that the Hubble parameter, it's 8 pi g over 3 times rho g, it's around 1 over m Planck squared, and the energy density rho is going to scale like t to the fourth. So during this epoch, we can write the Hubble parameter as approximately t squared over m Planck. So we can write this as t freeze out squared over m Planck. So MPL just means m Planck here. Okay, so now we can eliminate this N equilibrium at freeze out estimate from these two equations, and that allows us to write down that, okay, so let's see if I can do this. Let's see if I can do this right on the first try. Okay, so eliminating this N equilibrium at freeze out here, we have, that is TF squared over sigma V m Planck times T MRE over T freeze out cubed MdM to the fourth. Okay, so we can cancel these temperatures, leaving just one factor of the temperature of matter radiation equality there. We can cancel, we can remove these 3 TFs, giving a 1 over TF there. So the result that we end up obtaining is that in order to get the right relic density, the criterion that we have to satisfy is that sigma V is approximately 1 over and then there's a factor which is MdM over TF. Okay, so you might look at this and say, okay, this is fine. So we have this dependence on MdM here. The thing that's a bit tricky here is that this temperature at freeze out also depends on the mass of the dark matter. Now, to get this strictly, you have to solve a transcendental equation. You need to solve for sigma V times N of equilibrium at freeze out is comparable to TF squared over m Planck. The thing is that because the number density at freeze out is dropping very rapidly as a function of temperature, because it has an e to the minus m chi over t factor in it, when you solve that transcendental equation, you find that TF is parametrically of order MdM, because once the temperature drops dramatically below MdM, the number density is exponentially suppressed. So really, so more careful calculation T at freeze out is about MdM over 20 over a fairly wide range of mass possibilities. I mean, I can go through this in more detail if people are interested, but it's broadly speaking, this ratio ends up always being a number that is order of a couple of tens that is not very sensitively dependent on the mass. So putting that all together, what you find, so this tells you, so up to order 10 numerical factors, the requirement to get the right relic density through this process is actually very simple. It barely depends on the dark matter mass at all. It just requires that you have an annihilation cross-section, which is parametrically given by this ratio, 1 over the Planck mass times the temperature at matter radiation equality. If you changed the amount of dark matter that you wanted in the universe by a factor of 2, then it would change the temperature of matter radiation equality by a factor of 2. And it would change the required cross-section also by a factor of 2. If we ask, what does that actually correspond to in terms of physical units? Then this is, so M Planck is about 10 to the 19 GeV, so about 10 to the 28 eV. The temperature of matter radiation equality is about 1 eV. So this is 1 over 10 to the 14 eV squared, which is 1 over 100 TeV squared. So very naively, you might look at this and say, okay, suppose, I don't know what physics gives me this cross-section. Everything I've done so far involves only cosmology, no particle physics. I've just said I need a rate at roughly this scale to get the right relic density. So, but you might say, okay, but I know how Feynman diagrams work. So suppose this cross-section comes from a tree-level Feynman diagram, and it has the form of some coupling for the dark matter divided by some heavy mass scale squared. Suppose that this is the kind of parametric form of my cross-section. So then that tells you that my mass scale, my appropriate mass scale for this new physics is whatever the coupling is times 100 TeV. So one way to get this is to say, suppose I have a coupling that is similar to the electromagnetic coupling, which is 10 to the minus 2, and a mass scale around a TeV. That works. This is known as the WIMP miracle, weakly interacting massive particle miracle. The miracle bit is just that the weak scale times the coupling is the weak scale divided by its coupling is parametrically halfway between the Planck mass and the temperature of matter radiation equality. So now, but you also don't, so there are two other things that you can take from this. You don't actually need to be at the weak scale to get this cross-section. I could have a cross-section that was naturally larger, but maybe this comes from a one-loop process, not a tree-level process. Maybe it's suppressed by some other way. Maybe I just have a very tiny coupling for the dark matter. I could also, now, you might guess from this that I may start to run into problems when I try to run this calculation for mass scales higher than 100 TeV, because then I would apparently need a strong coupling in this sector. And indeed, you can make that formal if you work out the upper bound just from unitarity on this cross-section and say, okay, suppose I saturate the unitarity limit, which is mass dependent, how high a mass can I get and still have this calculation work? The upper limit is a mass of a couple of 100 TeV. So that was the upper bound of the thermal window that I drew on my plot before, where I said it failed at about 100 TeV. You generally have to modify the cosmology in some non-trivial way in order to get this particular scenario to work for mass scales much above 100 TeV. But between about an MeV and 100 TeV, if you get this cross-section, you'll have pretty much the right relic abundance. So that's one example of how we get the right relic abundance with a cross-section that is not particularly surprising from a particle physics perspective. And as we'll talk about tomorrow, if something like this picture is true, then there's a whole range of other experimental signatures that you can look for, which is of course why it's exciting to physicists, or part of why it's exciting to physicists. And a particular implementation of this kind of scenario is supersymmetry, where the lightest supersymmetric particle naturally couples to the standard model particles with strength set by electroweak couplings and a mass scale that could be not too far away from 1 TeV. And so this mechanism just works in that case. But of course, we haven't found supersymmetry at the LHC, so we'll see what happens there. Are there any questions about this case? Or about how we did this estimate? This like from here to here? Or Yeah, okay, so this step was, so I took these two equations. So this equation is coming from requiring that the energy density in radiation be similar to the energy density in dark matter, of matter radiation equality. This step comes from, this piece of the calculation is the requirement that, that is the condition for freeze-out. So this is relating the Hubble parameter at freeze-out to this scattering term at freeze-out, and then rewriting the Hubble parameter in terms of the temperature at freeze-out. And then I just took these two equations, and if I did it right, just substitute. So then I can write n equilibrium at freeze-out as Tf squared over m Planck sigma v. So then I just substituted this expression for n equilibrium at freeze-out from this equation into that equation. And that gets me to this result. And then if I canceled everything in the right order, then I get this result. Make sense? Good. Yeah, and again, you can do a cute exercise to do if you want to check that you understand this, is rerun this entire calculation where you have more than 2 dark matter particles in the initial state. If you have n dark matter particles in the initial state, what you end up finding is that you end up with, well, the object that now plays the role of the cross-section no longer has dimensions of 1 over mass squared. It has dimensions of 1 over mass to the 5 for a 3-body final state, 1 over mass to the 8 for a 3-body initial state, 1 over mass to the 8 for a 4-body initial state, etc. And so what you find then, when you do the same calculation here, is all that changes is that you get, well, okay, there's, yeah, sorry, no, I'm being a big glib here. Because I'm being a little bit glib here. There is a mass dependence that comes in as well, but when you work out what the implications that has for the overall mass scale of the problem, you find that, so in this case, the characteristic mass ends up just scaling as the geometric mean of the Planck mass and TMRE, but you find for n greater than 2, this expression just generalizes and becomes, it basically has extra powers of TMRE in this geometric mean. And so what happens as you go to more and more dark matter particles in the initial state, the natural mass scale for the interaction just goes down. So for 3-body, the natural scale, instead of being at 100 TeV times a coupling, is more like 1 GeV times a coupling. So if you have 3-body annihilations, the preferred range of masses is much lower, and more so as you go to higher body annihilation. Of course, if you want the higher body annihilations to dominate, you usually have to find a way to forbid the annihilations involving a smaller number of dark matter particles. Okay, yeah?
So you mean as a effect of bringing down the resistance, very massive particles of around TeV, right?
Sorry, so I...
At the end of freeze-out, there is a massive particle around TeV.
So the picture here is that the dark matter's like being around, I mean, the dark matter's present in the universe. It's being produced by collisions of standard model particles. It's being annihilated by collisions with other dark matter particles that go into standard model particles. And the rate of that depletion, provided that the rate of that depletion is given by a cross-section of this general size, then you'll get the right abundance almost independent of the dark matter mass. But if I then say, okay, I want to fit this into some particle physics model, what would be the natural mass scale to get this cross-section? Like, it doesn't matter how you get this cross-section from the perspective of the cosmology. But if you ask what would be a natural mass scale to get this cross-section, one way to do it, like if you say, for example, I'm just doing some S-channel annihilation or some T-channel annihilation, and I ask what's the typical mass of the particle in the mediator, then the scale that you want for that is 100 TeV times whatever the coupling is.
Is it possible to have it to crop solution?
So if you have TeV dark, so if you have heavy dark matter at this end, then more or less structure formation works fine. There are some questions about whether at the smaller scales this kind of cold, slow-moving, heavy dark matter gets all the details of structure formation right at very small scales, but those are also the scales where what the ordinary matter is doing is most important. And generally, as our treatment of ordinary matter in simulations has gotten better and better, the results have gotten more and more close to reality, even without assuming anything for the dark matter except that it is cold and collisionless and only interacts by gravity. So this, if I have a 10 TeV dark matter particle that has the right abundance at late times, you know, its velocity tends to be very small. Even if its momentum is pretty high, I'm dividing by 10 TeV to get the velocity. So it tends to be pretty slow moving. It has a low temperature. If I have only weak scale interactions, like what you need to get this annihilation rate, they don't really modify its structure formation behavior at all. I mean, you won't have dark matter subhalos lighter than about 10 to the minus 6 solar masses for a classic WIMP up at the TeV scale. But at the moment, what we can constrain is like 10 to the 7 solar masses. So many orders of magnitude away from the kind of little tiny clumps that are the smallest clumps you would get in this kind of scenario. So yeah, I mean, this is sort of the archetypal cold, collisionless dark matter model if you've got dark matter that's this heavy with only weak scale interactions.
It's worth pointing out that this famous argument, when applied to the only particles we know about, namely baryons, gets the answer wrong by...
Indeed, yeah, good, yeah, so good, yeah, so we made the assumption here that the dark matter was annihilating against other identical dark matter particles. But of course, that's not how it works in the standard model. If you do the same argument, assuming that like for electrons and positrons, assuming that there are equal abundances of electrons and positrons, then they don't all annihilate away. There is a residual abundance, but as Subia says, it's many, many orders of magnitude below what you actually observe in the universe. So what happens in the standard model is that there's a fundamental asymmetry between the matter and the antimatter, and this annihilation process starts off, but what ends the annihilation is not this freeze out, is not, it's not just what you run into is the problem that you run out of positrons. So in this sense, while it's the interactions with the standard model that are setting the dark matter abundance, it's actually still kind of a coincidence, that factor of 5 difference in the relic density between the dark matter and the standard model. Like they're both coming through, you know, some standard model involving process, but as far as we know, those processes are completely independent of each other. This is coming through a feature of the weak scale interaction cross-section being halfway between the Planck scale and the temperature of matter radiation equality, whereas we don't know where the standard model asymmetry comes from. We don't know exactly what happens in baryogenesis, but there's no reason to think it's particularly related to this. So there are models of asymmetric dark matter where the dark matter also has an asymmetry, which is related to the standard model asymmetry. And you can do the calculation similarly. In this case, basically you need a cross-section that's larger than this so that you run out of positrons before you hit this, you run out of anti-dark matter before you hit this limit. But yeah, I mean, that's also like perfectly, I like those models actually because they sort of attack head on this question of why are the abundances so close to each other. But yeah, I mean, in that case, you always want a cross-section that is larger than this cross-section. So that also kind of pushes you into a particular mass range. Okay, was there a question over here?
Yes. Besides the number of dark matter particles in the annihilation, what are some differences between quadratic models?
Oh yeah, so there are many ways to iterate on this. So of course, one thing to do is just say, okay, there are many ways just to get this cross-section. So if I don't change anything else about the cosmology and I just want how many different models are there that can get me this cross-section, there's an enormous profusion, like different masses, different couplings, different particles, other than the dark matter. The dark matter, one variation is the dark matter doesn't have to annihilate directly to standard model stuff. It could annihilate to other particles, dark photons or something similar, that subsequently decay into standard model particles. So long as the decay is fast enough, it doesn't really change anything about this picture, but it can dramatically change the signatures at late times in Earth-based experiments. Another, as we just said, asymmetric dark matter is a possibility. A sort of more general variation of that is maybe something like co-annihilation, where the dark matter requires some partner particle to annihilate in the early universe. And so then there are 2 number densities in these evolution equations, one for dark matter and one for the partner. You can have, if you just like stick to this scenario, it can still be true that this cross-section is not velocity independent. So this was the cross-section during freeze-out, but it doesn't have to be the same as the cross-section at late times. Again, this doesn't really change the freeze-out story, but it dramatically changes the late time signal. You can go in either direction. There are simple particle physics models where the cross-section scales like v squared. So at late time, I mean, the dark matter is pretty close to relativistic during freeze-out. It's non-relativistic, but not by a large factor. So if this scales like v squared, then this rate can be pretty high at freeze-out and completely negligible in the present day when v is 10 to the minus 3 times c. Or you can go in the other direction. If the dark matter is interacting through exchange of some light mediator, that gives you a velocity-dependent enhancement to the annihilation rate. And so you can have annihilation rates at late times that are much larger than you would have at early times. You can play around with the cosmology, and people do this especially to get this scenario to work for dark matter well above the 100 TeV scale. I made an assumption here that every factor I was dropping was order 1, but there are factors in these like number densities of radiation which depend on the number of relativistic degrees of freedom in the universe. So the usual problem if I tried to do this for say a 500 TeV or PeV particle is that I can't dilute the dark matter enough. I end up with too much dark matter in the universe because it can't annihilate well enough. One way to get away from that is if there were extra degrees of freedom early in the universe, so extra particles that we currently don't know about, well above the TeV scale, if those particles annihilated away after the dark matter had decoupled from the standard model, after freeze-out, and they heated up the standard model bath and put more particles into the standard model bath, but didn't do the same to the dark matter, then that effectively dilutes the abundance of dark matter, and it can reduce it so that you don't overclose the universe anymore. So you can play with modified cosmologies. People also think about like more radical modifications to cosmology, where you had, say, some like early period of matter domination, and then you have to change this calculation because I assumed everything was happening during radiation domination. Those models are interesting, and they might have gravitational wave signatures that you could see in something like LISA. I think that's probably the only way to probe them because you're usually positing something weird going on in the cosmology at very early times. So that's sort of some sets of classes of ways to modify this, but there are quite a few. Does that help? Okay. Great, so then in my remaining 10 minutes, let me start talking about the other example that I want to tell you, which is sort of the other classic dark matter production scenario, and that's Accion dark matter. And then we'll return to this WIMP or WIMP-like scenario tomorrow when I talk about how we actually go after these particles on Earth. Okay, but let's first talk about another example. Of axions and axion-like particles. Okay, so I'm going to give a fairly brief analysis of the motivation for axions here. So a reference that you can use is Michael Dine's TASI lectures. This will be more the particle physics motivation, and I'll talk about the cosmology here. These notes are pretty old, as you can see, but for the theoretical motivation, I think they're still pretty good. Okay, so what's the theoretical motivation for the axion? So the standard model Lagrange, this is what's called, so much of the theoretical motivation beyond this kind of thing could exist. How do we look for it is what's sometimes called the strong CP problem. So the basic problem here is that the standard model Lagrangian should, in principle, contain a term that looks like this. Where this G here is the gluon field strength. So this is like an E dot B mixing, it's a CP violating term, but we know that there is CP violation just coming from the quark sector of the standard model, so this strong CP violating term should in principle exist. There's no particular reason for it to be 0. So, but if this term is present, it would induce a neutron electric dipole moment. And the size of that neutron electron dipole moment can be computed. And you get a number that looks like this. You might say, okay, this is, yeah, sorry, I am missing a theta. Times theta. Now, so in principle, you might say, okay, you know, this looks like a small number. This is fine. But observations of neutron electric dipole moments are very, very good. And I think these are probably not even the latest bounds. These may be a couple of years out of date, but so they may actually be stronger than this now. But this suffices to make my point. Experimentally, this number is bounded above by this. So that tells you that this theta parameter controlling the size of this term should be smaller than about 10 to the minus 10. And there's no obvious reason in the standard model for this to be true, like for this number to be so tiny. So then the question, the strong CP problem is, why is this so small? And the basic idea of the Axion solution, which is, in my view, probably the nicest solution to this problem, is to say that you should replace theta by a dynamical field, which I will call A, but I'm going to put a tilde over it just to distinguish it from the scale factor, because otherwise when I do the cosmology of this, it's going to be a pain in the neck. So I'm going to call this field A tilde with a normalization, with a dimensional full normalization factor of 1 over FA. So an A is the Axion field. And then the idea of my mechanism to solve the strong CP problem is that I can, so this is the field 1 over FA as its coupling to G term. So my idea is that by making this a dynamical field, if this field evolves in a potential, it can naturally evolve to a small value. And so then theta will be set to effectively 0 dynamically, not as just some fixed result. So okay, in order for that to work, you need this axion to have a potential that it can roll down. So you can derive an effective potential for A tilde, for which I'm going to just refer you to Dine's notes. You can ask my colleagues here in this room. If you already covered the strong CP problem in Michael's lectures, then well, this can be a quick review. So there's an effect. So it turns out that there's an effective potential for this field, which you can get from those notes, which looks, it's a cosine potential through its interactions with the QCD sector, which looks like this. So parameters in here, f pi is the pion decay constant. At least this is true once you're down below the QCD once you're down below the QCD scale. And these mu and md are the masses of the up and down quarks. Okay, so this is a cos potential. This is nice. It means it has a minimum at a equals 0. That's the minimum that we want to roll down to. So let's look at the behavior of the field around that minimum. So we can see, I mean, this is a cos term, so it's going to have a minimum at 0, and then it's going to be a quadratic potential around that minimum. Okay? So the coefficient of the a squared term in this potential is going to give you the axion mass. So when we expand this potential term in the Lagrangian, we're going to get something that looks like we're going to get something that looks like a parameter times a squared. That parameter is going to tell us the axion mass. It gives us an axion mass that is set by the pion properties divided by the axion coupling times this prefactor that just comes from the quark masses. And again, this is pretty easy to get just by expanding out the potential. So everything in this expression can be estimated except Fa. So what we end up finding is that this corresponds to an axion mass of about 0.6 millieV. So I'm picking numbers out of the air for my normalization here. It will become apparent in a little bit why I've chosen these numbers. But the important thing that I want you to take away is that the axion mass is proportional to this 1 over Fa factor, which governs its coupling to the standard model. So as we go to lighter and lighter mass axions, they also become more and more weakly coupled. Now, as we've just seen, that's a really good quality for a dark matter candidate, because light particles that have significant couplings to the standard model that we're in thermal equilibrium with them are very ruled out. So we want it to be true that as we go down to low masses, we get into a regime where the particle just doesn't couple very much. So this relationship is good news for us. So I should allow some time for the next lecture. So I'm just going to say some general things, and then we'll wrap up for the day, and we'll do the axion cosmology at the start of tomorrow before heading on to how you search for axions and how you search for WIMPs. So okay, so higher mass implies a larger coupling in this framework, and consequently lower mass also implies a lower coupling. So the questions we need to answer. So the first is, okay, we want this to be a dark matter candidate. If it's very light, it's also very weakly coupled. That sounds promising. Question 1, for any dark matter candidate, if I'm building a dark matter model, the first question I want you to answer is it actually stable? I mean, we have an interaction here. This theta has been replaced by A over Fa, so there's an A G tilde term. That means it seems like in principle the axion might be able to decay into 2 standard model particles. So this is the first question, what's the lifetime? That's going to set one set of constraints on the axion abundance. It turns out, and this ends up requiring that the axion mass is less than about 20 eV. Question 2 should be probably your second question about light dark matter, given what we've talked about today, is was it ever in thermal equilibrium? Again, there's this interaction, like it's right there, you can't get rid of it. It's A interacts with the gluons in the standard model. How it interacts with the other particles is model independent, and so exactly what constraints you get like on this lifetime does depend somewhat on how it couples to the rest of the standard model. So so this is somewhat model independent, but these general ballparks should be pretty good. So it turns out that the answer to this is yes, if the mass of the axion is heavier than about 10 to the minus 3 to 10 to the minus 2 eV, and no otherwise. So if we want it to be 100% of the cold dark matter, we need to be in this regime. So now we're looking at pretty light particles. We need to be lighter than roughly the milli-eV scale for the axion to be a viable dark matter candidate. So this points to, and if it's that light, it will also be stable. So this points to milli-eV or lighter axions as DR. So when you're talking about milli-eV or lighter axion particles, their wavelength, you can work it out, it's sort of like bigger than the size of your lab. Their wavelength can be macroscopic, so you should think of it more as a wave or a field instead of a particle, and that affects how you look for it. In the early universe, this very light mass implies a very high occupation number, and so when we do the calculation at the start of next time, instead of thinking about these as individual particles, we're going to consider the evolution of a coherent classical field in the early universe. So it'll be fairly different. But let's leave that for tomorrow, given the time, and thank you very much. Any last questions? Okay, well, if you come up with questions overnight, save them for me and ask them tomorrow. I'll be happy to answer them then. Okay, thank you very much again.